I am pleased to introduce Josh Saxe from Sophos, who will be talking about security AI in the real world. Please welcome him.
Thank you. Can you guys, I'm not super loud. Can you guys hear me okay? Or, yeah? Okay. Okay, so, hi, I'm Joshua Saxe. I'm currently chief scientist at Sophos, and my talk today is entitled Security AI in the Real World. Okay, so the reason I submitted an abstract for this talk is that I think that right now AI and security is in this weird state where on the one hand there's a lot of hype and confusion and you know, almost any new security product comes with some marketing around the fact that it uses AI in some ambiguous and hard to understand kind of way. But then at the same time, there really is something there with respect to AI and security. I mean, we're seeing AI make real material impact in a whole range of fields, right? So probably many of us read about AlphaFold, which came out of a team at Google that made an enormous step function and progress towards predicting the three-dimensional structure of proteins, which is a significant advance in science. Many of us have probably also followed news about GPT-3 or played around with GPT-3, those of us who have access to the OpenAI APIs for that. And that's like a real advance, right? We've made real progress at machine learning models modeling language in ways that are likely to be really helpful. Some of you guys have probably played around with DALL-E, this new model that can draw images based on natural language prompts. And again, this is an example of a real technological advance. So my goal in this talk is to help separate the signal from the noise here, right? So if you walk around the trade floor at any security conference, you're going to get a lot of noise, to be honest, around the role of AI in security. But there really is a signal there. And so I hope that this talk can be a small contribution to helping the security community sort of get at that signal and get a grip on the ways in which AI is important now to security and will be increasingly important, I'll argue, in the future. Okay, so just so you know, a little bit about the human being here giving you this talk. My current job is I'm chief scientist at Sophos. That's the role I've been in for the last 5 years or so. Really, that means that I'm responsible for AI research, development, and operations at Sophos. I have a bunch of colleagues here today who are also giving talks about work that we've done here, and looking forward to you guys getting a sort of deeper dive from their work as well. Before that, I spent a bunch of time in the government world. Most of that time I was living in DC, working on mostly DARPA-funded R&D projects around applying mathematical modeling, stats, and machine learning to cybersecurity problems. My real background is like in the 1990s, like IRC hacker scene. That's where I learned probably half of what I know, and that's how I arrived, in the tech industry. And I studied something else in school. I did history for undergrad and grad school, and also studied music. If you're interested in ideas that I'm talking about here, please read Hillary and my book. It came out a few years ago, but still relevant, called Malware Data Science from No Starch Press. And then a little bit of background about the sort of professional context that I'm coming from here. So Sophos is a fairly large cybersecurity company. We defend about 500,000 organizations from cyber attacks. That we cover about 100 million endpoints. So the data science projects I'm going to be talking about today address that scale. And Sophos has security products that cover really every major category of security products, from firewall to cloud security, email security, endpoints, mobile security. And we have machine learning operating in almost all of those products. Actually, I would say every one of the products that isn't really sort of a legacy product, we have machine learning in. So that's just some context for the perspectives I'll be giving today. All right, so I want to like state my theses up front here. And the theses really revolve around where, like, the reality of where machine learning is in terms of what its strengths and limitations are in the way we do cybersecurity today, and then where I think it's going. These are my opinions, so I wouldn't attribute them to anybody else, but I think we have some level of consensus on my team at Sophos and among sort of security data scientists, friends I have at other companies. So here are the theses. So first, with where machine learning is today in the security industry, I'd say applying machine learning to a security problem is actually a last resort. It's the last thing you do after you do all the easier things, but it's almost always necessary. And I'll talk more about that in a little bit. I'd also say that contrary to, I think, a lot of marketing and I think popular perspective, in security ML, the actual math is the least important part typically. It's all the other surrounding factors that really drive accuracy and efficacy when it comes to security machine learning. Data engineering, and you'll hear more about this from my colleagues in other talks that are going to happen in this room subsequent to this talk, but getting the right data in the right place, correctly labeled as good and bad and that kind of thing, that's super important. How you monitor machine learning models in the field is super important. So there's all these surrounding factors that are actually more important than the math. You need to get the math right, but then it's these other factors that really drive accuracy. And then in the last part of the talk, I'm going to talk fast so I don't run out of time and I can actually get there. I'll talk about where I think the role may be in terms of these larger models that we're hearing about in the news and the tech press, like GPT-3 and that kind of thing. I think that those models are going to be really important, and I think it's our job as cybersecurity professionals and some of us as researchers to figure out exactly how. I also think a tighter feedback loop between security analysts and machine learning models is going to be a big part of the future of the way we use machine learning models. I think we're going to see something more like the Amazon recommendation engine or the Google search system come to play in security, where you have this tight feedback loop that operates at the scale of days between security operators making decisions and machine learning models making recommendations to them and prioritizing alerts and that kind of thing. So that's the argument I'm going to be making, or the set of arguments I'm going to be making. Let's get into the actual material now. Okay, so I think we come from diverse backgrounds here, so I just want to baseline on what I mean when I say machine learning. And let me see if I can point to things. Yes, I can. Okay, on this slide. So here's like the basic metaphor for how machine learning works in security. And I'm going to be talking about sort of the slice of machine learning supervised machine learning that matters most in security today. Basically, so in this example, we're building a malware detector. So if I want to build a machine learning malware detector, I get a bunch of examples of malicious software and benign software. Let's imagine we have .exe files in this case. And then I extract some numerical features from each one of those binaries. And my goal here is to build a machine learning system that can detect previously unseen malware. So in this example, I've kept it really simple. I'm extracting on the vertical axis a feature I'm calling file compression. It's just a measure of how compressed each file is. It might be a proxy for whether the file is packed. On the depth axis, I'm extracting the number of printable strings in the file. Maybe fewer means that the file is less likely to be obfuscated, might be benign. And then I'm extracting file size, just as another feature. Just to be clear, this is fake data. Unfortunately, the malware detection problem isn't so simple, right? What you're seeing here is that the red dots, which are the malware, mostly fall on this region of what we call the feature space, this three-dimensional volume in which I'm plotting my data. And the benign files mostly fall on this in this region of the space. Now, the machine learning problem here is to identify a geometrical structure that divides the malware from the benignware. So we call this a hyperplane in machine learning. And the mathematical problem is to identify the position of the plane and its angle so that we're separating between these two classes. And now the way we use the machine learning system is if we see a new, previously unseen exe file, we use some math to check which side of this decision boundary, which side of the hyperplane we're on, and then if we're on the malware side, we define it as malware. We're on the benign side, we define it as benignware. So for those of you who are like new to machine learning, if you understand this basic setup, you're most of the way there to understanding what we do all day as security data scientists, right? We build models that place security relevant observations, be they URLs or web pages or email attachments, into a numerical kind of space, and then we identify these separating boundaries that sort of codify the pattern that defines what's malware and what's benign. Now, in the real world, it's a lot more complicated than that kind of, data science 101 example. We're actually combining lots of different technologies when we deploy a machine learning model. So we're using signatures and allow lists to suppress false positives on the malware side, and we're using signatures and block lists to suppress false negatives on the benign side. And we actually have to use these supporting technologies to make a system deployable in the real world. And to get back to the point around how machine learning is really a last resort in security, really, if you're designing a security system, say, to detect macro-bearing email attachments, really, machine learning is the last thing that you do in defining such a system. So here's a notional but fairly accurate representation of the way that we would detect macro-bearing malware, let's say from the Office suite at Sophos. So first, we would just decide whether or not the observation, so the observation being a document here, is in an allow list. Like, is this document in an email from a trusted sender? And if so, then we just allow the document. Then we decide if it violates policy. Maybe the Visual Basic code inside the document does something that's just policy violating that we don't allow at our company. If so, we just block it. Then we check if the sender is in a block list, like a known malicious emailer. If so, we block it. So we make all these sort of really obvious decisions first. When we get to the end, that's when we apply on the tiny trickle of documents that have made it through this gauntlet of filters. These are document files that are in the gray area where we really don't know if they're malicious or benign. That's the point at which we apply a machine learning model and decide if it's good or bad. And this is typically, so sometimes you'll hear from security companies that they're AI based, or they're AI, that they're an AI first security company or something. The reality is nobody deploys, and if they do, they shouldn't, machine learning models without all of these guardrails and checks. That's really the place that machine learning lives in today's security pipelines. Okay, so why aren't practitioners who do security data science just building machine learning models that detect malware versus benignware, say, or malicious documents versus benign documents, or malicious behaviors versus benign behaviors, and just leaving it at that? And why are people using these guardrails and auxiliary technologies? And the reasons are, at least, these are some of the reasons. First of all, machine learning is really hard to control. So every time at Sophos we train a new machine learning model, or actually, every time we retrain a machine learning model that we have out in deployment on new data, we really don't know what kind of animal we're going to get out of that training process. Maybe all of a sudden this new model will, like in the malware case, FP on system DLL files that the previous model hadn't been FPing on. Maybe it'll false negative on a lineage of malware that the previous version detected. There's sort of a random black box nature to the way machine learning works in practice. That means it's very hard to control. It's also very hard to understand machine learning models. And that's the point about them being opaque and basically impossible to explain. So if our machine learning models are, say, FPing on sports web pages, in the case of machine learning models that look for malicious web pages, it's extremely hard for us to explain, or nigh impossible to explain, why that's happening. We can have some theories, but modern machine learning models are usually black boxes. That makes deployment really hard. It means that we have to do really, really rigorous testing on our machine learning models before we send them out to our tens of millions of endpoints. And it's also just hard because of the reasons I just stated. It's hard to redeploy machine learning models because every time we retrain them, we're not quite sure what we want to get. We have to go through a whole battery of tests before we're actually comfortable sending them out into the wild, where they're blocking files from executing and doing potentially dangerous things in our customers' computers. So in contrast, older-fashioned methods like signatures and policies are really clean and easy to operate relative to machine learning. When I define a signature that detects a certain malware family, I know exactly what I'm writing, as opposed to opaque machine learning models. The outcomes are well controlled. The signatures that we write and the policies we write are explainable. And as a result, signatures and policies are just these tactical Swiss Army knives Like at Sophos, we deploy new signatures on an almost daily basis to our customer base, whereas machine learning models we deploy about once a quarter. So I'm sort of bashing machine learning here, which is ironic. I'm a security data scientist. I want to talk about why we almost always deploy machine learning models in our systems, even though they're so hard to deploy. And really, it comes down to efficacy. So here's I think an example of what I'm talking about. This is a timeline showing the accuracy of our Windows malware detection system that we have in our endpoint product at Sophos. And what you're seeing here is that in this, I guess, 6-day period in July, our signatures caught, to the best of our ability to estimate, about 90% of malware we observed on our endpoints. There was a dip here on July 8th. Our machine learning system detected about 95% of the malware, sometimes a little bit better. And when we combine those systems together, we did the best, of all three scenarios. 96 to 98% detection. So the reason security companies are moving to using machine learning is that it's not that it's a silver bullet. It's that to squeeze the sort of last 5 to 10% of accuracy out of our detection pipelines, you really need machine learning. This is what I think all of our colleagues across many companies are finding. So machine learning is very difficult to deploy. There's lots of downsides to it, but it provides added value on top of all the technologies we had before we sort of took this machine learning turn in cybersecurity. Okay, so that's my intro. Now I wanted to go through our journey on our team around building a machine learning program over the last 5 years. Just as a not to promote ourselves, but as a case study, just as we have insider knowledge here that we want to share with the community. And happy to take questions when I get through this section around any details of sort of what we've done and lessons we've learned from this process. Now, 5 years ago in 2017, at the beginning of that year, we had 0 machine learning models in deployment at Sophos across our 100 million or so endpoints at that point in time. And then since then, up through 2022, we've integrated machine learning all throughout our portfolio. So at this point, we've got more than 30 machine learning product integrations at Sophos, and that's sort of swept across our whole portfolio. So this is just a chart showing sort of where we've deployed machine learning and how many integrations per product category we have within our portfolio. So what exactly are we doing with machine learning at Sophos? And I just want to say that I've got friends at other large security companies too, and they're doing similar things with machine learning. So this is fairly representative of where machine learning is being used in the security industry in general. So our first use case with machine learning was to detect Windows malware. That's like the big heavy-hitting case in which machine learning is getting used in lots of different places, not just at Sophos. Then we moved on to build models that detect malicious email attachments like Excel, PowerPoint, and Word documents. We have machine learning that operates on Android endpoint devices, detecting malicious apps. A bunch of different detection models that detect basically the major hitting categories of threat vector types. We also use machine learning in the context of web content filtering. So we have a model that looks at URLs. For data scientists in the audience, this is a character-level convolutional neural network. And then we have another model that's, if people are interested in the paper reference, I'm happy to share, but it's sort of convolution-like that operates on HTML, JavaScript, and CSS. Then we have some models that we use to help explain detection results to users that, for example, when we detect a file as malicious, show the most similar files in our database that are also malicious versus the most similar files that are benign, and let users sort of understand why we detected that file. And models that we're working on currently are more user-facing. So you'll hear a bit more at BSides from our team about an alert prioritization model. We also call this a case escalation prediction model that operates in a kind of feedback loop between analysts and the machine learning model and predicts which alerts SOC analysts will decide are truly malicious. And we're working on some natural language interface stuff also with machine learning. So that's just sort of the sweep of places that we are applying machine learning at Sophos. So not all problems in security, really far from it, are machine learning problems or are appropriate to solve machine learning are appropriate to apply machine learning to. So here are some criteria that we use to define what constitutes a good nail for the machine learning hammer. So one, the distribution has to be relatively stable. So what do I mean by that? So the distribution of like malicious PE files versus benign PE files, for example, even though that changes over time as attackers evolve their behavior, it's a fairly slow-moving change that we see. And what we've found in our research is that things change slowly enough in that world, and we have enough data that we can model that problem and ship a successful machine learning model. An example of a distribution that doesn't fit these criteria are, for example, insider threats, where you're trying to detect whether or not a user is stealing data from a company based on their user interaction behavior. In our opinion, humans are too unpredictable. We don't have enough training examples, and so less appropriate as a problem for machine learning. We also need reasonable deployment and operational complexity. So, for example, we've thought about shipping models that look at a whole bunch of different factors spread out over sort of different layers of the compute stack all at once. So, for example, you might want to look at, I don't know, like a PE file's behavior in conjunction with its static features, in conjunction with like the URL it was downloaded from. That sounds like a good idea to have a machine learning model reason about all of those observations all in one place and make like an optimal decision. The reality is it's incredibly hard to get all of the data feeds required. It's integrated in one place in order to build such a model. It would be very hard to actually do the engineering work to integrate a model across all observation points that you'd need to deploy such a model. It's just too complex. We found keeping things really simple and just looking at like a certain file type or like look at web pages and training a model in isolation on those observables, while it might not seem conceptually as optimal, it turns out to be the right approach just because of the operational complexities. So those are just some examples of how we think about where it's appropriate to apply machine learning. Okay, so here's our current organizational structure, which I think is important to talk about. So we have a research department on our team. So we've got about, I think, 30-something people on our team right now. We have a research department. You're going to be hearing from a bunch of these people at BSides. That's about a dozen people or so. We have 2 program managers. So I think when people think about machine learning and security, they mostly think about applied mathematicians and researchers. But I think the one takeaway from this chart here is that actually the majority of our team are not applied mathematicians and researchers. We've got these other categories of professionals on our team. An important team here is program management. So we have 2 program managers and an intern there right now. That's extremely important in a company that's shipping security machine learning models because of where machine learning sits within a large engineering organization. Basically, in order to do our jobs, we need to pull down data from probably, depending on how you count, a dozen other engineering teams within our company, use those, understand those data, load them into the database that we use to train and monitor all of our models. And then once we've trained our models, then we ship those out to like a dozen different teams. So we are a central node in this sort of web of dependencies. And it's because we need to get data from places, and we just ship models to a bunch of other places. And so we need program managers to help tame the chaos of actually doing that in a reasonable way. And then we have this large, at least relative to our research and program management teams, engineering organization that's responsible for integrating lots and lots of different data feeds from lots of different places, from feedback from our products, third-party threat feeds that we subscribe to, lots of different places, loading that into a very large-scale, sort of petabyte-scale database, retraining models, and that's really where most of the work of an operational security data science team happens, which is why this is a fairly large organization. And here's just a really high-level diagram of our data architecture. I mean, I think the one thing I want you guys to take away from this here is that most of the complexity of our team exists in this data architecture. What you're seeing here is that we pull down lots of data feeds, like I've been saying. It goes through a complex infrastructure, ends up in Snowflake. And then there's a whole bunch of compute infrastructure that we're using to train and evaluate and package up and ship our models on the right side. We have a dashboard that's constantly evolving, but that we use to monitor model accuracy. Our ops team is sort of looking at that and looking for dips in accuracy. And when we have an issue, right, we spot it and we work on retraining or understanding what the issue is and getting a new model out there that works better. A big part of our team's sort of routine work is retraining all of those models that we have out in deployment. So we try to retrain them once a quarter. After a quarter or so, their accuracy really starts to degrade because they are modeling observations of benign and malicious observations in the past. And obviously, cybersecurity changes really rapidly. This is where we monitor our retraining schedule in Confluence within our team. And then finally, for those of you curious about the actual math behind our machine learning models, and I'm not going to spend too much time talking about that, here are just some example architectures that we are currently shipping. So to detect malicious URLs, we're using a convolutional neural network. And basically the way this works is we, at a high level, the neural network looks at the raw character string of a URL and learns what patterns are important in terms of detecting malicious URLs, and then makes a prediction as to whether or not the URL is malicious or not. At a lower level, what we're doing is we are sliding these kind of windows over the character string, and we have 1,024 neurons that sort of slide over the character string looking for patterns. You can think of them as kind of like elements of a regular expression, and they activate when they find something of interest. And then we have some feed-forward layers that sort of, you can think of them as doing a kind of non-discrete if-then-else logic over the patterns that have been identified by the convolutional units, and they decide whether or not the URL is malicious or not. So that's just one example architecture. We've got papers about all of these models out there. If you guys are interested in looking, happy to share. It's probably hard to write down these links from the slides, but happy to share links for anybody who's interested after the presentation. We've got another model, which is a kind of original architecture we came up with that looks at web content, that also uses that same kind of, it's called a convolutional approach that looks for patterns and then reasons about the sort of confluence of all the patterns and deciding whether or not a web page is malicious. And then we're using a newer transformer model to detect malicious emails, like phishing emails and that kind of thing. So I'm not going to go into detail there, but transformer models use a kind of attention model in which the neural network is sort of deciding what's important in an email and sort of choosing to focus on the important bits and deciding whether or not an email is a phishing email. So we use a lot of neural network models within our team. We also use a lot of decision tree-based models, like based on XGBoost and random forest and that kind of thing. So here's I wanted to also give a kind of slice of life in terms of how we retrain and ship new models on our team. So here's how we retrain and ship our Windows malware detector. So first, the engineering team within the organization I manage trains our Windows malware detector on new data, but also including old data. Basically, we look at like a recent window of about 100 million plus files that we've seen, both malware and benignware. So we train that model. And then the engineering team passes that model. They do their own internal tests on the model, and then they pass it off to the research team that signs off on it, depending on how the results look. Then we send that model downstream, and you'll notice we do a ton of testing on these models. So then we send it downstream to another team that's external to our organization, an organization of like domain experts who do malware reversing and signature rating and that kind of thing. And they also look at the results and they validate the results. Then we ship the model to some subset of our customer base, but millions of endpoints, and we sort of continuously roll it out until we hit all of our endpoints. And we use it to perform inference on new PE files, but we don't actually block any PE files yet. We're just kind of auditioning the model. And finally, when an external validation team decides that the model is behaving in a reasonable way, then we start rolling it out and turning it on. And we do that in chunks. So we do like a fraction of our customer base, and then another fraction. And finally, the model is actually operational and blocking PE files from executing that it thinks are malicious. But the point here is we do a ton of testing before we actually ship and deploy a new model. And that's because of all the things I mentioned earlier. The fact that machine learning models are opaque, hard to understand, random, unpredictable, but they're also good, and that's why we put all this work into them. They also detect stuff that we would never have detected otherwise, but we have to do a ton of testing before we actually turn them on. Otherwise, you get into situations where you are disrupting customer businesses because you're false positiving on files that that they actually need to run their organizations. Okay, so just sort of, well, let me stop here. I think this is a decent breaking point, and just see if there's any questions, if I can clarify anything, any comments. Please go ahead. Yeah. 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 Okay. So the question was, so the colleague here deals with machine learning compliance and that kind of thing, and he's asking if we do any introspection into the machine learning models. There are some well-known techniques like SHAP and LIME that you can use to help explain machine learning predictions. He's wondering if we use those techniques. I mean, I feel like I should really defer to my team here, but just for convenience, I'll just say, just because I'm up here, basically, we trust this validation process much more than we would trust like a LIME explanation as to what our model is doing. The issue with any of these explainability approaches, I would say, and this may be a controversial position, I'm not sure, but is that they are models of an opaque model. And as such, well, they are interpretable models of non-interpretable models, right? And so, like when you, so let me explain like how LIME works, for example. So LIME, it fits a linear model to the predictions of a nonlinear model, and linear models have this nice property that they're basically summations of a. So if I was to fit a LIME model to our PE model, basically what I would read out is that, oh, these three features seem to be contributing to the PE model deciding this is malware or not. Now, that might be really satisfying to see that the LIME, this LIME model, gives this interpretable explanation. Whether it's really true or not sure. It's a linear approximation of a nonlinear model, right? Whether that explanation generalizes to a new example that lives in some other part of the feature space, who knows? We do use those techniques sometimes to make sense of what our models are doing, but with a lot of caution and with the sentiment that these are shedding a little bit of light into the sort of fog of uncertainty that we're living in, but not clearing the fog. The benefit of this process that I'm showing on the slide is that we're actually testing the models on the scale of millions of customers in silent mode and seeing how they would behave were we to turn them on, and just building confidence at scale, right? So they're both important, but yeah. So I think that was a really good question. Thank you. Yeah, question back there. So the question is, do we implement our own models, or are we using existing implementations? If the question is like, are we computing gradients like from scratch? Like, no, right? Like we're using PyTorch and that kind of thing. Or like we use PyTorch, we use XGBoost, and we use sklearn. Those are like the main tools that we use in our team. On top of that, we're building, like in the previous slide I showed, right? There's lots of original ideas in here, that we published as our own papers, but yeah, we're using the same toolkits that everybody else uses to actually implement this stuff. Yeah, please.
I did have a question about the case study for the phishing emails.
Yeah.
Because you said you're using transformer models, and usually just the text of the email wouldn't be really enough. You have a lot of rich metadata that also incorporates. So I was wondering if you could share some of your best practices of how to combine these two.
Yeah, that's a great question. Yeah, so the colleague here asked. The comment was, given that we're using transformer models, which focus, at least the sort of stock form of a transformer model, in the natural language domain just focuses on text, a text document? Are we also incorporating like email header features, since those are obviously a helpful signal in the email domain? So yeah, it's a really good question, and that was like the question that we were pursuing when we constructed this model. I would say you can look at our paper on how we do that, but basically this very simple diagram shows that we are using a bunch of transformer blocks in our phishing detection model, but then we also add in near the final layers of the model, we add in a bunch of context features, and we do find that helps. So we are using header features in conjunction with the text features. Thanks for the question. And maybe one more question? Yeah, please go ahead.
For your validation process,
Yeah.
describe that a little bit more.
Yeah.
Like, is it manual or
Yeah. Yeah, so the question was about, I was asking for more detail on our validation process. So like the basic, we could spend a whole talk on that. So yeah, that's a very good question. I should also say, I mean, I don't know, probably 2/3 of our time on our team and the research team goes into setting up validations, scrutinizing validations, mistrusting our validations, and questioning whether they're even accurate or not. And that's a huge piece of all this. I mean, one basic thing that we do constantly is time splitting. So we train, you can think of this as a kind of historical simulation. So we train a model up to some time t, and then we pretend that we had it in deployment, and we look at data that we observed afterwards, and we see how it behaved over time, and also in a ROC curve or a precision recall plot to show how it would have behaved over some time window. And anyways, that's sort of a standard design pattern for how we design basically all of our validations. Another problem is the timeliness of the labels. So the more time you wait, the more accurate. Typically, the more time you wait, the more accurate your good bad labels become. So sometimes we go back in time and look a year back or something to see really how well do we think this model is doing based on that sort of time, what you earn from putting that time delta in. But there's no perfect answer. I mean, there's a lot of intuition and domain expertise that goes into this too, because it's cybersecurity and you're never going to have perfect labels. Okay, I'm going to keep going, and so we'll have more time for questions later. Okay, so I want to sort of drive my points home, hopefully not to the point of annoyance here, but so I just want to talk about some myths and realities in security machine learning. So one, I just think people talk about the math as though it's the main driver, and it's really not. It's all these other operational questions that we're talking about and that came up delightfully in the questions that people asked just now that really go into driving accuracy. Like you need to understand the math, and you need to be able to pick a good modeling approach. But that's like the easy part. Like the hard part are all these operational details, like what the colleague asked about validation, what others asked about introspection, and understanding what your models are doing in the fields. Those are the hard parts. I would say, I mean, we come up with original ideas that we're proud of, but those squeeze like a few % extra accuracy out of a problem. Really, if somebody's claiming, if like a security vendor is claiming they've got some like fancy new math or something, like I think they get negative points for that. Usually it's like the basic ideas really that, like if somebody's going beyond what's available on Wikipedia, then you really have to ask why, and they need to really show their credibility. You can do pretty well with already existing knowledge, and also doing a really good job at the operational questions. And then the final thing is, I mean, for a while people in the industry, and I think even now still, we're talking about machine learning somehow superseding signatures or obviating SOC analysts and domain experts, obviating block lists and allow lists. The reality is those technologies are pillars of the way we do security today. And as a security data scientist, I'll say we rely on those tools as part of a broader ecosystem in which we integrate our technology. So I think I've gone over most of this. I'll just say, so like a big problem is correct data labels. I mean, so if you're not, so it's garbage in, garbage out when it comes to these models. If you're not labeling malware and benign-ware correctly, you're gonna be way off in terms of the model you actually deliver to protect people. If you are training a model on data that's not representative of the networks that you're actually trying to defend, it's not gonna work. It's not gonna generalize to those new networks very well. You really need data that reflects the context in which you're deploying your model, both the attacks and also the benign observations. Designing a good evaluation that accurately predicts how well your model will do in deployment is absolutely critical to machine learning security R&D. Your team doesn't have a compass to know where north is if they don't know how well the model will do when you deploy it. And this is a huge problem with a lot of security data science research. And again, you need these other tools like signatures and allow lists and block lists to deploy machine learning. I wanted to say a brief note about why people ask us a lot about whether or not we're addressing the literature in adversarial machine learning. So for those coming here outside of data science, so there's a literature on what's called adversarial examples in machine learning today, and the idea of an adversarial example is it's a human-crafted input to a machine learning model that's deliberately designed to confuse the machine learning model and give an incorrect prediction. And there's lots of clever and fancy ways that you can come up with these examples. Maybe some of you have seen, for example, pictures of like a school bus that look like a school bus to the human eye, seem to be completely untampered, but that a computer vision model will like just undeniably assert is a flamingo. That's like an example of an adversarial example. Now, there are people doing work on this in the security domain showing that you can craft, say, exe files that bypass a machine learning detector. We currently, as a practically oriented security data science team whose mission is to defend real-world customers today, are not focused on trying to defeat these kinds of examples. And there's a couple of reasons why. The first one I would say is that our machine learning systems sit inside of a big, complex decision pipeline that involves a lot of non-machine learning layers. I think that the threat model that a lot of the adversarial ML literature focuses on in the security space really is just focused on the machine learning model in isolation. But we're focused on maximizing accuracy over this entire detection pipeline. And it's just not clear to me that adversaries will have such an easy time getting past all the other layers if they are adding adversarial sort of sugar to their malicious PE examples. The other, at least that's half the reason that we don't focus on adversarial ML right now in our research group. I would say the other half is just practical. Like, we have so many other leverage points we need to improve on to improve our models. Like, some of our models, we ideally ship them every quarter, but they slip a quarter. We have data feeds from, critical, in many of our models, we're integrating half a dozen data feeds all in one place, and we have data feeds just going out, and maybe we don't notice for a couple of weeks. I mean, in the practical reality of our team, improving all of, moving all those other levers just has to take priority over this research. But I thought putting this slide in there might just be a good point for discussion here, because I know a lot of people in our community are interested in these examples. We read those papers, we're just not focused on, it's just not our top priority right now in terms of coming up with ways of getting around adversarial machine learning. Yeah.
Just 1 second. Sorry to interrupt.
Yeah.
If you guys have any questions from the audience, we have a wireless.
Oh, thanks. That's really helpful. Thanks a lot. So in security data science, the focus of the discussion is usually on feature selection and mathematical modeling. The reality is the life of a real-world security data science team encompasses all of these nodes in this kind of placemat map of security data science work that I've created here. To know whether you're doing a good job, you need to know, you need to be able to have a good answer to the following questions. Where do you get your training data from, and why do you think it's representative of the data you'll see on a real network? How do you know what good and bad look like in your training data and your evaluation data? These are all hard questions. How do you fuse data from multiple sources to get the best possible training and evaluation data? We need to know, so for the algorithms you're using, I said the thing about Wikipedia already, but how did you design your evaluation, and how do you know that actually predicts accuracy on a real world network? If somebody's presenting to you machine learning work they've done, you want to see their evaluation. If they're showing you accuracy numbers, you want to know all of the nuts and bolts behind how they did that evaluation, because evaluations are biased. You also want to know if somebody's proposing to you that they have a really good security machine learning system, you want to know how it integrates with allow lists, block lists, and signatures. There's all sorts of questions that you want to ask. And then there's their operational picture. So there's the question of how do you monitor accuracy and deployment. A lot of the efficacy of a system hinges on that. how do you deal? Do you have procedures for dealing with accuracy crises with models that are out there in the field? How often do you train and retrain your systems to make sure they're fresh, reflecting the changing threat landscape? These are all the questions that are sort of outside of the domain of like the math and the feature space that are really important to the actual efficacy of a security data science program. Okay, so last section of the talk, I want to talk a little bit about where, and this is just my own opinion, really, like where security machine learning is going to go over the course of the next decade or so. Okay, so I would say a key result in machine learning, thank you, 10 minutes, okay, gotcha. A key result in machine learning over the last 5 years is this idea of neural scaling laws. And so I want to illustrate what that looks like, and this is sourced from a paper from Google that came out, I think, a month ago. Basically, the basic idea behind neural scaling laws is that as we make neural networks bigger, even if we don't have any more clever ideas, even if we simply just scale up the width of the layers of our neural network, magic things happen. So we do better in accuracy, and even new capabilities emerge in those machine learning models. So here's an example from a research team at Google in which they trained a model to, it's funny, as I said that, my Google Assistant thing just came on. Now it's off. Okay, so this model was trained to take a sentence of natural language text. So in this case, a map of the United States made out of sushi. It is on a table next to a glass of red wine, and translate that sentence into an image. And what they showed in this figure is that they took the same model and sized it as a 350 million parameter model. So 350 million parameters basically means there are 350 million interconnections between like the neural units in this model. And what came out at that scale was this sort of visual gesture at a map, a weird kind of cubist red wine glass, and like what looks like something vaguely sushi-like over here. So it didn't really work, right? But then with no new cleverness or no new ideas, but simply sort of adding scale to this model, they scaled it up to 750 million parameters. And then you really do see some sushi. This looks sort of Alaska-like, or I don't know, my geography is not very good, but it looks like sort of map-like, and you just have something closer to a glass of wine. Anyways, point being, by the time you get up to 20 billion parameters, you really do have a map made out of sushi, and you really do have a glass of red wine, and you really do have a table. And so this is a really robust result that's come out of machine learning research in the last 5 years or so, that in a whole bunch of different domains, as we scale neural networks up, they acquire new capabilities. So here's another, for a data scientist audience, you probably have seen this, but another really powerful example. So here, another team at Google scaled a language model up to a ridiculous degree. I think this was, maybe somebody remembers better than me, I think 300 billion parameters or something like that. So absolutely massive. You need like a room scale supercomputer to run this model. But they asked it to do a whole bunch of parlor tricks, which were really impressive. One of which was to explain this joke. So the joke was, did you see that Google just hired an eloquent whale for their TPU team? So TPUs are special machine learning processors that Google's developed. For their TPU team, it showed them how to communicate between two different pods. And so then the model responds, TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. The joke is that the whale is able to communicate between two groups of whales, but the speaker is pretending that the whale is able to communicate between two groups of TPUs. So it's really impressive, right? That a machine learning model was able to give this description. And this same model has a whole bunch of other capabilities that are equally impressive. And again, what's happening here is Google is using a model much like the phishing detection model that we're using on my team at Sophos, but it's just at a scale that's truly massive, and capabilities emerge when you scale models up to that degree. And so you can see, I mean, if you get into this large model stuff, you can find really wild results. Like here are a bunch of images generated by that Google model I showed earlier when it scaled up to 20 billion parameters. And it just has an enormous visual vocabulary, and it's able to see the relationship between the vision domain and the text domain. So these are all images that it generated based on textual prompts. Here's an example of a model writing code based on the prompts. Many of us are probably familiar with like the Copilot model from OpenAI that you can now use to do this. Now, how is this relevant? I know I have a few more minutes, so I'm going to go really fast. How is this relevant to cybersecurity? So here's an example that a colleague and I came up with, showing how you can use the GPT-3 large language model to categorize domains. So I gave it a prompt. So I said list of websites and their content categories, and I gave it some examples, like berkeley.edu is an education domain, Amazon is shopping. I gave it 5 examples. And then I gave it a new example that was syntactically quite different from the previous examples, and I just asked it to autocomplete my example, and it autocompleted it as weapons. So it got it right. And so actually, in our web detection technology right now, we use tens of millions of examples. And what's noteworthy here is that we used 5 examples and showed them to GPT-3, which has like 200 billion parameters, and it just got the answer right? That's impressive and it's relevant to cybersecurity. Here's an example from malicious domain detection. So I give it 4 examples, and I asked it to categorize a syntactically totally new domain. I mean, I just made this up. It doesn't actually exist in the real world. And it gets it right that it's BAT, right? So I think these large models have something to offer us in terms of a kind of tactical maneuverability around our models. I mean, it took me 5 minutes or probably a minute to create this model, and now it's detecting malicious domains. And that's, right now there's all sorts of practical challenges actually using this technology in the field. It's costly to do inference on GPT-3 and all that. We couldn't deploy this at scale in our customer base. But I do think this is a sign of what's coming in terms of the applicability of those large models. Just because I only have a few more minutes, I'm going to skip through some slides here. The other place, and I think do I have time for questions after my time's up, or I do? Okay, that's great to hear, so I'll go a little slower. The other place that I think security machine learning is going and needs to go is around a much tighter feedback loop between users and machine learning models. So the modality that we've seen around the deployment of machine learning in general in the tech industry has been that users fulfill their intentions with products. Let's say Google Search is the product that we'll use as an example here. Machine learning models, in turn, learn to anticipate and fulfill user intent. So when you start typing into Google, I don't know, restaurants in Vegas, like within the first 3 characters, right, it's predicting your query. And oftentimes, you don't have to type the full. I mean, I almost never type the full query, right? You just click on the recommendation. And users have come to expect this kind of collaborative real-time relationship with machine learning in their engagement with products. And as a result of companies successfully implementing that, more users use the product. And there's this sort of virtuous cycle between users using products deriving trading data from that, and products ultimately improve as a result of this cycle. So we see that in recommendation engines. We see that in information retrieval. What we're working on in our team, the more forward-looking thing that we're working on, is creating that kind of feedback loop in a security context. And so you guys will hear a presentation about that today after my talk. But basically, we've got a team of about 100 SOC analysts at our company that actually protect our customers' networks as part of a subscription service. And we're sort of setting up that feedback loop between SOC analysts and the alerts they look at, and recommending alerts that we think they're going to find to be true positives. I'm not going to go too much into the results here since I have 2 more minutes, and you're going to hear about those later. But we're finding that it's really efficacious. And surprisingly, there are very few examples of companies deploying these kinds of systems yet in security. And I think that security over the next decade is going to catch up to the Amazons and Googles of the world and creating those kinds of user ML feedback loops, but within security products and services. So just to reiterate some takeaways. So with current ML, security ML is both the last resort because it's so hard to deal with for all the challenges because of all the reasons that I described, but almost always necessary. The math is usually the least important part. It's all these contextual problems. I think there's a real future for large models. I think it's the role of security ML researchers to figure out exactly what that future is, but I think those are going to play a part in security going forward. I think feedback loops between users and machine learning are going to play a part. I think adversarial ML is an important area to look at going forward, but today and in the short term isn't a priority. It's all those other questions that I brought up. So thanks a lot, and looking forward to feedback. So it sounds like we have time for questions, so please go ahead.
Not a question, just something that was very unappreciated. Is a library called Cleverhawks. Never heard of it. If I have trouble shooting, cleverhawks.io. Put that out there.
Yeah. Yeah, so cleverhans.io is a good place to go to learn more about adversarial ML. Yeah, thank you. Other questions? Yes.
Besides the new data engineering team on the work with small companies, and you mentioned about the kind of black box models, I guess. Do you have anything that's analogous to like traditional CM software development?
So what was what was the last part of your question? Oh, CI/CD.
CM system, yeah, for configuration management. Do you have a model like keyword parameters?
Yeah. So the question was if we're using anything like a configuration management system with respect to our data engineering operation. I'm gonna look to folks, my colleagues here from Sophos, and I don't think so, right? No, we're not at that level. We're not that sophisticated yet. Yeah. Thus far, no. But yeah, let's talk afterwards. And yeah. Yes, go ahead.
What if you're using your stock analyst in a feedback loop for your prediction on the next on what's escalated, like escalated? So are you using your stock analyst's data labelers? And if so, are they flagging or tagging?
Yeah.
Marking certain bits of data as a specific reason?
Yeah, so the question is, are we using SOC analysts as data labelers? So the folks sitting next to you actually are going to be talking. So Ben and Adarsh will be talking about that. So yeah, I mean, like the answer is it's like yeah, but it's like super complicated, and you can't just it's complicated how you do that. So yeah, stick around in this room if you want to hear more about how we're doing that. So yeah, okay. Well, please one more question and then yeah, go ahead. Yeah, so we have a paper out about, so the question was about how we do detection on HTML and JavaScript. I mean, the short answer is we're doing it in like a traditional end-to-end deep learning way. So it's format agnostic, the way we do it. And the representation is learned, via stochastic gradient descent, style optimization. But the longer answer is I should share a link to our paper because we have a paper that describes the method by which we do that. So thanks. So yeah, I think let's disperse. Anybody who has any more questions, you can come talk to me or maybe my team would be happy to answer some questions too because there's some folks from Sophos AI here too. So thanks everybody for coming, much appreciated.